Hi, everybody. Welcome to this webinar, which is organized jointly by the KNAW, the Dutch Royal Academy of Sciences, and the Dutch Organization for Logic and Philosophy of the Exact Sciences on causality in economics, computer science, logic, and language. We are delighted to see so many people joining. And today our hosts, we will be running this webinar, are Rineke Verbrugge, professor at the University of Groningen and a member of the KNAW and a member of the VWL, about which I will say something in a moment. And myself, also a member of the board of the VWL. So I don't think I need to say much about KNAW because probably many of you know, but I wanted to take a moment to say something about the Dutch Association for Logic and the Philosophy of Exact Sciences. Because this you might not have heard of before. Actually, the VWL was founded a long time ago in 1947. It's almost 76 years ago, to promote the study of logic and the philosophy of the exact sciences in the Netherlands and to increase collaboration between scholars in logic and philosophers of the exact sciences in the Netherlands and abroad. Logic, of course, is an interdisciplinary subject which lies at the intersection traditionally of philosophy, mathematics, linguistics, and also now lies at the foundation of computer science and artificial intelligence, which has many contemporary applications. And the VWL represents logicians in academia, but also everyone with an interest in logic, both pure and applied, and philosophy of the exact sciences. And we organize events, we support initiatives in the field, and we are also a de facto alumni organization for logicians. And even at the age of 76, we are still very much alive. Currently, we have almost 240 members, and we have regular activities such as Logic at Large Day for a general audience public lecture, events for PhD students in logic, master thesis prize, and outreach activities. And today's webinar is one of the outreach activities. And if you're interested to learn more about this organization, or you would like to become a member, then please visit this link, verenigingvoorlogica.nl. So then I wanted to say something about the topic of the webinar today, which is causality. Now, of course, causality is a timeless topic in science and philosophy. Causality, the study of cause and effect. And it has received actually quite a lot of attention in recent years. And for example, in the last 10 years, many different textbooks on the new textbooks on the subject have appeared. I'm just showing a few of them here, including a book by Guido Imbens, who is going to be speaking today. And I wanted to touch very briefly on a few different themes that are in causality, that are actual, and that will also relate to the talks that we will see today in the webinar. And one is, of course, everybody who has, taken a statistics class or a methods class in the social sciences is familiar with the adage, correlation does not imply causation. And you might, some people have taken this to mean that you cannot draw causal conclusions from observational data, that trying to do so is inherently methodologically flawed. This is, of course, not the case. And in fact, the Nobel Prize in 2021 for economics went to Professor Guido Imbens and Joshua Angrist and David Icard for their pioneering work on deriving causal knowledge from observational data in the form of natural experiments. So that's something that we will hear more about today. Another theme is causality in artificial intelligence. So in artificial intelligence, we do, one of the things we do is machine learning. We train models from data and use them to make predictions for previously unseen data. And one thing one often sees in practice is that model performance drops when the model is being applied to data that does not look like the data on which the model was trained. So for example, a model for medical diagnosis trained on data from one country might not generalize if the model is being applied in another country. maybe because the different diseases are prevalent in different countries. This is just an example. And in machine learning, we say that a model is robust if it is not sensitive or not so much sensitive to this kind of distribution shifts, and or the model can be adjusted or fine-tuned to new distributions easily. Now, it turns out that this model robustness is which is an active topic of research, is closely related to understanding causality. And so one way to analyze model robustness is using causal inference. So this is one way in which causality is actual as a theme in artificial intelligence these days. Another theme is much older in some sense, is that if you ask yourself, what does it really mean when we say X caused Y? What does a sentence of the form X caused Y really mean? Well, one classic way of understanding the meaning of causality is through counterfactuals. These are sentences in natural language of the form, if X hadn't happened, then Y would not have happened. Or if X happened, then Y would have happened. So an example of this is if Oswald hadn't killed Kennedy, somebody else would have. Well, that's a sentence that's could be true or false. Probably it's false. But contrast this with the sentence, if Oswald didn't kill Kennedy, someone else did, which has a very different meaning, of course, presumably is, of course, is true. So so the sentence of the first type is called a counterfactual, and you can see this from the word would, or the subjunctive mood. And so counterfactuals are a classic object of study in logic and the philosophy of language, dating back to the 70s by the work of David Lewis and Robert Stalnaker and other famous philosophers. And so in this sense, causality is really ingrained in certain ways in which our language works, in certain linguistic constructions like subjunctive mood and others that we will also hear more about today. So, so in this sense, causality is a topic that has its roots also in philosophy of language. So those are some of the themes that we will see also today, and we have a very nice lineup of speakers. The first speaker, well, I will leave it to Rineke, our other host today, to really introduce all the speakers, but we have a very nice and distinguished list of speakers here, covering different aspects of causality as is in the title of the webinar, in computer science, social science, philosophy, and in language. The way that this webinar is organized is that we will have 4 talks, and then we will have a plenary discussion afterwards. This means that if you have questions about the talks, you can ask them in the chat. Please do. We encourage people to ask questions in the chat, and then we will try to cover as many of them as we can at the last part of the meeting, the last half an hour. So I have a few more remarks on practicalities, which is, as I mentioned already, if you would like to ask questions, please use this, actually the Q&A option in the menu bar below the screen. And then if it might be good to prefix your question with the speaker that you are addressing. So if you have a specific question for one of the speakers, start your question by the speaker's name. And then we encourage you to keep your questions short and to the point so that we can address as many of them as possible. And if you are watching on YouTube, because this webinar is being recorded and live streamed both in Zoom and in YouTube, we will not be watching the chats in YouTube, so only in Zoom. Okay, that's all I wanted to say, and then I will I will give the word to Rineke Verbrugge, who will take it from here.
Thank you very much, Balder. I'm very pleased and honored to be able to introduce to you our first speaker, Professor Guido Imbens. Professor Imbens was born right here in the Netherlands. He did his high school here in the Netherlands, Then he studied economics at Erasmus University in Rotterdam, inspired by the Dutch economist Tinbergen. But then he moved to England to do his master's in economics and econometrics at the University of Hull. And he then moved even farther away to do a PhD at Brown University. After that, he briefly came back to the Netherlands to teach at Tilburg University, but then he moved to the United States with such luminous universities under his belt as Harvard, UCLA, Berkeley, and now finally the Stanford Graduate School of Business. Professor Guido Imbens has made a great impact in economics, among others with his work together with Angrist, drawing causal inference from observational data and introducing the idea of natural experiments. Their joint work led to their winning of the Nobel Prize in Economics in 2021. We are very honored that Professor Imbens will speak to us about causality today. The floor is yours.
Thanks very much, Rineke and Balder. Thanks very much for inviting me to talk here. So let me actually share my screen. Hold on a second. Okay, it's a great pleasure to be here. This is a somewhat intimidating audience for me. I'm not a philosopher, so I'm not quite sure exactly what to expect. But by the same token, it's a very interesting audience from my perspective. I'm really looking forward to the discussion later and the other talks. So what I want to do is give you my perspective on causality and kind of more generally how many economists and other social scientists as well think about causality in the research we do. Of course, you should keep in mind that economics is not a monolithic field, and there are different approaches to doing empirical work being pursued in economics. But the perspective I will talk about is certainly one of the more common ones in economics. And so let me start by talking a little bit about where I'm coming from as an economist. Kind of a long time ago, economics was perhaps closer to philosophy. Great economists from the past, such as Adam Smith and Alfred Marshall, perhaps Keynes, were philosophers as much as they were economists. But recently, that's changed a fair amount. Kind of recently, Al Roth and Esther Duflo, kind of both Nobel laureates in economics in the last 10 years, have written about economists as engineers and economists as plumbers, kind of arguing for a less exalted view of economists, where economists try to address kind of much more specific, so arguably more narrow social problems. In the case of Al Roth, a colleague of mine here at Stanford, he studied matching markets such as those for kidneys, where some people need kidneys, some people are willing to provide kidneys, but they would really like particular people to get kidneys and they may not be a match with them. And Al Roth kind of developed methods for ensuring that people would supply those kidneys, even if the people they wanted them to get the kidneys didn't necessarily get them, but through trading. And so economists kind of, in those cases, solve very specific problems about how to get the resources to the people who need them in the most effective way. And that kind of more narrow view of economists as engineers or plumbers is kind of more the tradition I fit in. Now, more precisely, what I do is econometrics. And really, what is econometrics? It's kind of hard to give a very clear definition, but here's an interesting quote. Statistical information is currently accumulating at an unprecedented rate, but no amount of statistical information, however complete and exact, can by itself explain economic phenomena. If we are not to get lost in the overwhelming, bewildering mass of statistical data that are now becoming available, we need the guidance and help of a powerful theoretical framework. Without this, no significant interpretation and coordination of our observations will be possible. Now, what year do you think this quote is actually from? Although this quote seems remarkably modern, and I can actually use this in my class, I could pretend I wrote it myself without changing a word. It's actually a quote from 1933 from Ragnar Frisch in his editorial for the first issue of Econometrica. Econometrica is the journal of the Econometric Society, was founded a couple of years earlier, and which was really there at the start of what is now known as econometrics. And so it's kind of a little curious really to think that Frisch would thought of the data available at the time as accumulating at an unprecedented rate and a bewildering mass, and it shows you to be a little careful with the word unprecedented. But so what I try to do, what econometricians try to do, is build frameworks, methodologies for making sense of data, whether that is a small data set or an overwhelming, bewildering mass of data. And often these frameworks are about separating correlation and causality. I think we all more or less agree on what we mean by correlation, but there may be less agreement on what we mean by causality. And my perspective on this is really rooted in two traditions. One in economics, going back to Tinbergen in the 1920s, and one in statistics, going back to Fisher and Neyman in experimental settings around the same time in the 1920s and 30s, and generalized in Rubin's work starting in the 1970s on observational studies. Rubin was one of the first to explicitly link causality to manipulation. I think Paul Holland in 1986 coined the phrase, no causation without manipulation. I think that has been a bit misinterpreted, but how I interpret that is that I think of causal effects as the effect of something, of a manipulation or an intervention or an action. At some point, there's a fork in the road where we can contemplate going down one path or another. And what we're interested in is the comparison of what lies at the end of these different paths. And that may be a real actionable manipulation or more of a hypothetical manipulation. Sometimes that's very clear, kind of in the early examples of Fisher and Neyman, when they were looking at the causal effect of different types of fertilizer. It's very clear. I can put one type of fertilizer on a plot of land or a different one, and it's clear what I mean by the causal effect. Similarly, I can take an aspirin or not take an aspirin. It's not quite so clear when I talk about education. I went to college, but what do I really mean by the counterfactual of not having gone to college? And sometimes it's very unclear. What do I mean by the causal effect of gender or race or obesity? In the case of obesity, I'm happy to think about the causal effect of exercising or the causal effect of going on a diet or the causal effect of surgery, but I don't find it very helpful to think about the causal effect of being obese of a state rather than something that is linked to an intervention or an action. And in these cases, I'm going to think of the causal effect really as the comparison of these potential outcomes. And because most of the problems I work on, we really start with the intervention, with the action. And so this perspective on causality isn't really very limiting. Now, given a question about the causal effect of some intervention or manipulation, randomized experiments are a very useful place to start. They allow us under fairly mild conditions to estimate some average effect of these interventions, and we know how to do the inference in those cases. So here it kind of is a very simple example. We have a population of 72 children. Some of them get assigned to get honey before going to bed and some didn't. And you can look at the effect of that treatment on coughing during the night. But it's often more difficult to do experiments in economics. We can do this sometimes, and especially in development economics, researchers have started doing a lot of experimental evaluations, including Esther Duflo and her co-authors. And there are also some very influential experiments done in other settings, some going back to the 1970s, when in the US, they did some large-scale experiments called the negative income tax experiments, where they experimented with different tax rates for different groups. But most of the time, we cannot do experiments in economics, and we rely on observational data where we don't have the guarantee that the treatment group and the control group are comparable in the absence of the treatment. And so what are some of the challenges with that? I want to highlight two of the challenges that are particularly salient in economics and other social sciences. I'll refer to those as agency and interactions. By agency, I mean that in economics, the units of analysis are often agents. They can be individuals or firms or countries. And these agents have objectives, and they act deliberately to further those objectives. In contrast, kind of to the passive units in the Fisher and Neyman type of experiments, who didn't have preferences over outcomes of treatments. Fisher and Neyman were looking at experiments where the units were plots of land. And the plots of land don't really care whether they get fertilizer A or fertilizer B, and they don't deliberately try to end up with one fertilizer rather than the other. But in economics, the individuals often care about which treatment they get, and they may deliberately choose to get preference for a particular treatment. So let me give two classic examples from economics. Suppose we're interested in the effect of education on earnings. We can't simply compare earnings for people with different levels of education and then interpret that as the causal effect of education. Education wasn't randomly assigned. Education was a choice. The choices reflect preferences and characteristics of the individuals. And it may be partly that it may be partly a choice anticipating what the causal effect of education on earnings is. People who get more education may be precisely those who benefit more from getting more education. And they may have had higher earnings irrespective of their education level. Similarly, suppose we're trying to estimate a demand function. That is the quantity that people would be willing to purchase as a function of prices. When we estimate a demand function, the problem again is that prices are not set randomly, and not even approximately randomly. They're set deliberately by sellers anticipating what demand will be. So you see, for example, that just before Christmas, prices for children's toys are high, exactly because demand is anticipated to be high. And just after Christmas, prices are low, because sellers know that demand is low. So economists worry about the treatment or the cost not being randomly assigned. Or in other words, they worry about agents making deliberate choices based on information that may not be available to researchers. And these choices are what lead to the correlations that are not causal in nature. We see that education is positively correlated with earnings, but we're not sure whether that's because high ability people choose to acquire more education, or because education has a causal effect on earnings. And so to deal with this problem, which is often referred to as endogeneity, economists built mathematical and statistical models both for the potential outcomes, but also for the choice of the agents in order to disentangle the correlation from the causation. And sometimes these models get very complex. Here's an example from an actual physical model of the economy, the monetary national income analog computer, or also known as the Phillips machine. This was built, there was a series of these machines built, of these models built in the 50s by economist Bill Phillips in England. Actually, and this one is one in Rotterdam where I was an undergraduate, but it's still where you can still see it. And so here, this was a model of the economy where you could figure out, you could simulate what the causal effect of various government policies would be by pulling levers and turning on faucets. You could see what the effect of that would be on GDP. Now, these machines kind of were a little sketchy in the sense that it wasn't always clear how credible the predictions of the effects of government policies based on these machines would really be. So let me turn to two more recent examples of ways in which economists disentangle correlation and causation, both from the natural experiment literature, where we're trying to make these inferences for causal effects more credible. One is from my own work in a study with Tom Rubin and Bruce Sacerdote. We were interested there in the causal effect of a universal basic income on labor supply. And so from an economist's perspective, the concern with the universal basic income is that it may take away the incentive for people to go out and find work. And we may worry that such effects are there, but we don't really know how big these effects are. And figuring out how big these effects are is very important for designing a social security system that is both fair and efficient. And so how would you estimate that effect? You could do an experiment, but that would be incredibly expensive and time consuming. Suppose we had an experiment with 500 people and we gave half of them 25,000 euros per year for 20 years. That would cost about 125 million euros. Now, how else could you do this? One thing that economists have done in this literature is compare labor supply for individuals with high earning spouses with labor supply for individuals with low earning spouses. That has its own problems. Spouses are clearly not randomly assigned either. Other things people have done is look at people's response to getting inheritances. But again, inheritances are not completely random and they're partly anticipated. So what Rubin, Sacerdote, and I did was go to the lottery. So we went to the lottery in Massachusetts, and they essentially did the experiment I just described for us. They randomly allocate large sums of money over 20 years to a bunch of individuals, one individual every week. It's not quite as simple as that. They don't actually randomly assign it to individuals. They assign it to lottery tickets, and there's still differences between the winners and losers. But at least it allowed us to get clear and credible estimates of the causal effects of unearned income. Kind of right here, some of the estimates are on the order of 5 to 10% reduction in labor earnings, 5 to 10 cents reduction in labor earnings for every dollar won in the lottery. Now, another example is from work by Josh Angrist. Josh was interested in the causal effect of class size on children's educational outcomes. Again, that's a very important question in educational policy. And but the question is how you would estimate that without doing an experiment. And Angrist exploited the fact that in Israel, there's a law based on an old Talmudic rule from Maimonides that class size cannot be bigger than 40. If there are more than 40 kids in a cohort, the school must split the class into two. And that creates the variation in class size that is unrelated to children's ability, that is a deterministic function of cohort size, but not related to children's ability. And that can be exploited to get estimates of the effect of class size on children's outcomes. Now, I mentioned before that there was a second challenge for causal inference in economics that is very common. Interactions or spillovers. Much of economics is fundamentally about interactions between agents. Interactions in markets, preferences for different choices being constrained by budgets. Now think about the standard experimental setup, where we have a number of units where some are assigned to a treatment group and some are assigned to a control group. The standard analysis assumes that treating one unit does not affect any other units. That's very plausible in many drug trials. I mean, it's not quite so plausible in vaccine trials, but in most drug trials, say if we're testing the effect of aspirin, whether I take aspirin or not doesn't affect anybody else's headache. But that type of assumption doesn't really work in many economic settings. Suppose, for example, that one of the rideshare companies, Uber or Lyft, wants to change their platform, the way the interactions work. It wants to change their app. Maybe they want to decrease the cut they take from drivers, or change the tipping policy, or something else. You could imagine doing an experiment where you assign some drivers to the new policy and some drivers to the old policy. But it doesn't necessarily work. If the new policy induces drivers to work more, then that affects the entire market. If the drivers are induced to work more, that means there are going to be more drivers on the road, and the experience for the control drivers is going to change. There's going to be more competition, and so their activity will go down. And so simply comparing control drivers and treated drivers is not going to tell us what would happen if all the drivers were in the treatment group relative to what would happen if all the drivers were in the control group. And so this type of spillovers requires a whole new type of experimental design, one that takes into account how the markets work, how market participants interact with each other, and how the actions by one participant in the market changes the experience for everybody else. In other words, that type of setting is going to require you to think about the economics of the problem, even in an experimental design setting. And you could imagine doing more complex experiments where you assign subsets of drivers and riders to the treatment group in a way that would allow you to disentangle these type of effects, to disentangle the direct effects of the treatment from the indirect effects coming through spillovers. So what economists worry about when we're trying to look at causal facts, and causal facts is what we're typically interested in, is both the fact that the agency of the units creates biases, that because the individuals are trying deliberately to affect the treatment regimes they're in, affects the comparisons we can make ex post, and the fact that spillovers create biases in comparisons between treated and control units. And we're kind of trying to use idiosyncratic variation in some of the assignments, as well as design experiments that can help us disentangle these things. Let me stop here, and thanks everybody for being here. And let me turn it over to the next speaker here.
Thank you so much for your fascinating talk about the view on causality from economics. That was really great. So now we are turning from economics to computer science. And I would like to introduce to you our next speaker, Sara Magliacane. And she has done her bachelor in computer engineering from the University of Trieste, followed by a master also in computer engineering at the Politecnico di Milano. And then she moved to the Netherlands and did her PhD in computer science at the Vrije Universiteit Amsterdam on her thesis about logics for causal inference under uncertainty. After that, she has worked as a postdoc, mainly at the MIT IBM Watson AI lab. And since the last 2 years, she is also working next to this as an assistant professor at the University of Amsterdam. So welcome, Sara, and the floor is yours.
Thank you very much for inviting me, and I'll try to represent computer science as well as possible. So let me try to share my slides as well. So this should be it. Okay. So I'm going to talk about causality-inspired machine learning, which is just the idea of using causality to help machine learning. And this can also help even if we are not able to reconstruct fully all the causal relations that we need, for example, because we don't have enough experiments. Or also if we are trying to learn causal variables from high dimension observations, for example, images, but we are not sure whether we have learned the correct true causal variables. We can still kind of use ideas from causality to help machine learning. So I'm going to give this working definition, which I think is, I would say it's probably the same as what Professor Imbens has just talked about in great detail, but just maybe to, connect a bit the dots. So I'm going to say that the variable x causes another variable, if changing the distribution of x, for example, by fixing the value of x, changes the distribution of y. And just to give you an example, a bit more practical, I chose this example. This is an example that I thought was appropriate today because we have Professor Imbens. So this is some old data from 2012, so it's a bit outdated, but we have on the x-axis the chocolate consumption in different countries in kilograms per year per capita. And on the y-axis, we have the number of Nobel laureates per 10 million people in all of these countries. So in 2012, and so this is a bit outdated, in the Netherlands, people were eating 5 kilograms of chocolate, more or less, per person, and there were around 12 Nobel laureates per 1 million people. And obviously, there is more now. And in Switzerland, people were eating more chocolate, so they were eating around 13 kilos per person per year. And there were also more Nobel Prize laureates. And now the question is, does chocolate cause Nobel Prizes? And, we can try to set up, a thought experiment. And let's assume we have some experiment and we are able to convince the Dutch government to try to suggest people to eat more chocolate. So in the Netherlands, people start eating more chocolate and nothing changes. In Switzerland, also they start eating more chocolate and nothing changes. And this happens for several countries. So this is just an example that if you intervene on a variable x, let's say chocolate consumption, so you change the distribution of x, and you don't see any change in the other variable, y, the number of Nobel laureates, then you would say chocolate does not cause Nobel Prizes. And let's assume there is a hypothetical universe in which things go differently. So now we are still, as the Dutch government is still asking people to eat more chocolate, and there is a dramatic increase in the number of of Nobel Prize winners. And this tends to happen also with other countries, then we would probably assume that chocolate causes Nobel Prizes. And this is just an example of this informal definition to get us started. So in machine learning, we often use this definition, and we call changing the distribution of x an intervention or a manipulation, as Professor Imbens just mentioned before. I think it's a very similar setting and terminology. And again, also here, the challenge is, as I think in most fields that try to do causality from data, we try to estimate the causal effect of an intervention that we didn't perform. And maybe we have some experimental data, not the ones we are trying to estimate, or maybe we just have observational data. And then often, at least in the type of machine learning I'm working with, we use causal graphs as a representation. So these graphs have the random variables I was mentioning before as nodes. So we have chocolate and Nobel Prizes, and they just represent causal relations. For example, in this hypothetical world in which chocolate seems to cause Nobel Prizes, we have an edge from chocolate to Nobel Prizes. And obviously, I just wanted to again mention causality and machine learning have a big overlap. There is a lot of work in machine learning to help causality, and there is also a lot of work in causality that can be used to help machine learning. So I'm going to focus on 2 cases, mostly how causality can help robustness and transfer learning, and a bit on reinforcement learning. But obviously there is a lot of different work. So I left some links there, but obviously you can find a lot of different works on this. So I wanted to go back a bit to the causal hierarchy. So the type of causality we work with is, at least the one I work with, is related to what Pearl is describing. And so Judea Pearl has this causal hierarchy that he proposes, in which there are 3 levels of causation. So the first is association, so essentially correlations. The second one is intervention. So similar to the chocolate example, we wonder what would happen if we eat more chocolate, what would happen to the other variables. And then there is a third level that Balder has already mentioned, counterfactuals, which are about retrospection. So for example, I had a headache, I took an aspirin, I was cured. What would have happened if I didn't take an aspirin? So if I took a different action. So I'm not going to talk about counterfactuals today. And I argue in this talk, and this is the causality-inspired machine learning part, that maybe in some cases full causality, in the sense of recovering the complete causal graph, so all causal relations, maybe it's not necessary, or maybe sometimes it's a bit too expensive, because we may need either assumptions or experiments, either to identify the graph, or in other cases that I will show, to identify from images which are the correct causal variables. And so sometimes we don't really need that. even if we do something light, so causality-inspired is like causality light, that would be still enough. And so causality-inspired machine learning is a bit on the interface between the first and the second level, but it doesn't necessarily go all the way to causality. And obviously, again, there is a lot of work. I will talk a bit about my work, which are some examples in domain adaptation, but there is a lot of work and I'm happy to share with you if you want to know about it. So I'll start with a toy example. So this is a toy example. Obviously, usually we have more measurements and more complicated examples, but I just wanted to give you a feel about what we're doing. So let's assume we have some data from some mice. So these wild-type mice are just mice which are not genetically modified. And let's say we have just measured two phenotypes, X1 and X2, and we have another phenotype, Y, that we want to predict. And we have the wild-type mice. So this is our source domain. And for them, we have all the data. And then we have a set of different mice which are genetically modified. For example, there was a gene knockout on gene A. And we also have X1 and X2 for each of these mice, but we don't have Y. So the label, the things we're interested in, Y, we don't have it in the target domain. And so the idea is we can try to exploit data from the non-genetically modified mice to see how we can learn about Y in the genetically modified mice. But we cannot do it directly because obviously the distribution changes between the different mice. So we want to learn a model on the source domain that can transfer to the target domain. So this is the setting. And we can see this from a graphical perspective. So we can add, for example, a context variable C. So for each not genetically modified mouse, we have a 0 for all of them. We have 1 for the ones which are genetically modified. And then we can put the data together because we are still able to distinguish them based on C. And then we're kind of, for now, this is simplifying, but we'll consider them as coming from a single distribution over C, X1, X2, and Y. And then we'll assume that this data can be represented with a non-causal graph, which includes also this variable C, which is the variable we call the context variable. And so this is not our contribution. This is relatively well known. And so we will just essentially build on this concept here. And I'll start just by explaining what happens if you do know the causal graph. So in this set, we're searching, we want to predict Y, and we want to predict Y for these genetically modified mice. But we want to do it from the wild-type mice, and we want to be able to only use features which will be giving us a bounded generalization error, so that when we predict in the new domain, there will not be like an arbitrary error, but we have a bounded error. And so we call these features separating features. There are other people calling it stable features or other names. And in this case, there are features, sets of features, which deseparate Y, this variable here, from the context variable C. So this separation is a concept in graphical models. For example, you can see the textbook that Balder was talking about, the book of Y by Pearl, or other books by Pearl, or books by Spirtes, Glamour, and Shines to explain it. I will not explain it because unfortunately I don't have the time, but just to give an idea, this concept, this separation, under some assumptions, tells us, given a graph, which conditional independencies are true in the data generated by that graph. So in this case, we have that Y and C are deseparated when we condition on X1. So I'm not going to explain exactly why, but this means that we can read from the graph directly that Y is independent of C given X1. And why would we care about this independence? Well, we care about this independence because if we have the source data, which are the green data, and we have also the target data, which are the blue circles, if we just use the source to fit this line here, the dotted line here, we would still be able to predict the target. And so this is a scatter plot between X1 and Y. So X1 is a good predictor because we're, in a sense, able to train or essentially learn a predictor on the source domain, and it seems to have a bounded generalization error on the target. And the interesting part is that if we know the graph, we can read this kind of statement from the graph that X1 is a good predictor. So let's try with X2 then. So because we have X1 and X2, right? So let's try with X2. So X2 is not deseparating Y from C. I'm also not going to explain exactly why, but this is what happens in the data. So we have x2 on the x-axis and y on the y-axis. And let's say we train on the source data, the green ones, we train this dotted line. When we're trying to predict the target based on this dotted line, we'll have a huge error, so potentially arbitrary error. And this is just an example. The target could be essentially anywhere. So this is known as collider bias. So when we condition on something that it's after the outcome. So again, this is not super new, it's just this separation is a way to think about it that people have been using. And so that's why we care about features that separate Y from C, if we know the graph. But obviously, if we know the graph, it's easy. People have done it for tens of years. But if we don't know the graph, then this is a bit more interesting. And also what happens if we have some missing conditional independence tests, because, for example, there are no labels in the target. And so this is what we have focused on in our work. We are going to extend the example from before. Now, instead of two sets, we have a multi-source domain adaptation. So we have two source domains. So we have two types of genetic intervention, like mice with different types of genetic knockouts. So we have two source domains. And then in this work that we did with all my co-authors and published at NIRP 2018, we showed that we can assume that we represent all of this data with a joint, a cyclic, not acrylic causal graph with multiple context variables, which is something we have also shown that, it's okay to do. And if we can represent it with this graph is still unknown for now, but we can still use methods to learn this graph based on conditional independencies, and we'll be able to find these separating features, so features that will be safe in the target domain. So this is what we are looking for, separating features in the target domain. We have some assumptions, for example, no extra conditional dependencies involving Y in the target domain and other assumptions. And then what we do is we take all the data that don't have essentially question marks, and then we do conditional independence tests on them. And if we have a certain pattern of conditional independence tests, we can show that then there is a set of possible causal graphs that fit the conditional dependencies, and then we can compute the d-separation that we care about on the set of graphs that fit these conditional dependencies. But because we can do this by hand, and we have a proof in the paper, so in this paper, add this link here. But because we don't necessarily want to do it by hand, we use a theorem prover. And so we use a logic encoding of this separation, which is based on answer set programming for the logicians there. And so we essentially use Klingo, which is a solver for answer set programs. And we kind of input the conditional dependencies, some assumptions. We have a query, this logic encoding of this separation. And then we try to see if a certain set, if a certain feature, sets of features is provably separating, which means it will give us a bounded generalization error, or provably not separating, or in some cases, we cannot identify. And so this is what we get. And we can iterate this for different sets of features. And this gives us an algorithm to find essentially sets of features which are safe. But there is a big, so this is, I really like this work, but there is a big issue with the current work. Currently, the work is not very scalable, also because of the theorem prover we use. So now I'm going to talk about a different line of work I have been working on, which uses similar ideas of using graphs to transfer things from different source domains to a target domain. And now I will talk a bit about reinforcement learning. So in this other work we did with my other co-authors, ADRL, which was published at ICLR 2022, we had a set of different source domains. In this case, we had this Atari game, if you remember, Pong. So we had a lot of trajectories from Pong. And then we have, again, Pong, but the domain was different because, for example, there was a rotation of a certain angle. And here we changed the color of the domain. So we're trying to do different variations of Pong to see that whatever we learn will be stable to these variations. And so given like that we had the position of the player, the position of the ball, the position of the adversary, the actions and the reward in the different domains, we could show that you can learn a causal graph in this time series in which you have things from time t-1 to time t. So this is a dynamic Bayesian network, if this makes sense to you. Otherwise, it's just a graph that repeats every time step. And so there is this domain shared representation, which we could prove had these links which were causal. And then we also were trying to learn these domain-specific parameters, which were constant in each domain. And for example, they were the rotation angle or the background, or also changes in the reward. So if we do it from symbolic data, it's interesting, but it's even more interesting if we can do it from images. So if we can do it from images, and OT is an image at the time step T, so then we're able to learn a representation in the latent space that had a graph, which was sparse, but we couldn't anymore say that S1, S2, S3 were the position of the ball, the position of the player, or anything else. So in that case, we couldn't really say anything about what these variables were, but they were still useful, and they still, as I will show later, they were still useful in trying to transfer to a new domain. So this graphical representation was still useful. And this concept of having some parameters that modulate different functions, like the context variables I showed before. So this was essentially the setup. We have some source domains. We estimate the graph I showed you. We had a way to reduce the number of state components and change factors to S mean and theta mean. And then we learned an optimal policy on the source domain pi star. And then when we're in the target domain, we see a new angle of variation. We're just in very few samples, we're able to estimate the new value of theta mean target. And also we're able to estimate the states, the latent states. And then we could just apply the policy we had learned in the source domains to these new values. And so there were obviously some simplifying assumptions with respect to the previous work, because to make it actually a bit more scalable. So we also didn't have any new edges in the target domain. So it was a bit simpler. And obviously the results are good. We outperformed the state of the art. And so these were like, the average final reward on these tasks, card poll and Pong, which are typical tasks in reinforcement learning. And we also had some ablation study in which we removed the graph. And then the graph showed that it was actually, if you remove the graph, it was actually worse. So the graph was actually quite useful. And we had a similar situation in a work we did on factored adaptation for non-stationary reinforcement learning. And in this case, we had a reinforcement learning agent that had to learn a policy that was robust to different types of non-stationarity in the environment, including multiple simultaneous types of non-stationarities. So to give you an idea, this is a typical setting in reinforcement learning. This is called the half cheetah. So I didn't manage to make the video work because I have a PDF, but just if you're curious, you can find it. So half cheetah is a problem in which you're trying to move the different joints of the cheetah such that the cheetah achieves a certain target velocity. And in this case, there is some wind going against it. And the non-stationarity, for example, is a sinusoidal wind. So whatever policy you learn on how to run, you should be able to handle the fact that there is kind of this latent wind that changes essentially how you can run. So you have to learn a policy that is able to adapt to that. And this is another example in which we had this robot called Sawyer, which had this reaching goal, and it was supposed to kind of go to this point, and we would be moving the point around. So this was both continuous and discrete. So in this case, we had a similar graph to the one before, but now the latent change factors had also, like, they were not constant anymore, but they had a Markov process between them. And we can show that the edges which are full can be identified, so we can learn the correct causal graph. But edges which are dotted, we're not sure anymore about them. But still, this seems to be useful. And so we have this setting. Let me just check. Okay, still. Okay, good. So we have this setting on how to learn this. So we called it a factor non-stationary variation autoencoder. It's not really that important. The idea is just that you're trying to reconstruct essentially the inputs from the trajectories you have collected. You're trying to see if whatever graph you learn and whatever thetas you learn are able to reconstruct well the next time step. And you know the next time, so you're able to kind of minimize that loss. So this was the idea. Okay, so in that work, we estimated the graph, we estimated latent change factors, and then we can learn a policy, and we consider just that these latent change factors are the true ones. So it was quite simple. And again, yeah, the results are that we consistently outperform the state of the art. And we can show, so these are the return. We are the red lines, and we're always above, so that's always better. And in the ablation studies, we show, and this, it's kind of not super visible, but there is a small pink square, which shows that essentially, if we switch off the graph, that's our biggest contribution. So the graphs are really, really useful for these methods to work, even if we're not necessarily sure that the variables are causal or that the graph is the true one. Okay, yeah. So this is, so this was the, sorry. Yeah, so this is the conclusions. So I'm at the conclusions, yeah. So essentially, I wanted to say that graphical models and these operations are a principal way to reason about imbalances and distribution shifts. And this is something that Balder has already mentioned. And again, not a new observation. People know it since a long time, and definitely since 2012 pretty explicitly. And this is also true if you don't know the causal graph, and even if you have missing data or zero-shot settings, as we had. And in our setting, we didn't need to reconstruct the causal graph. We could bypass it with the theorem prover to instead prove a missing conditional independence. And so I thought that was interesting. So causality is useful as an inductive bias for the theorem prover to show that you can prove some conditional independence. And in general, these ideas are empirically useful, even if we cannot guarantee that we're learning the true causal variables or the true causal graph. So that's it. And actually, probably no questions later.
Yes, so thank you very much. That was really fascinating and very exciting results. And indeed, the questions will be completely at the end in the plenary discussion. Yep. I would just like to say to the attendees, you're completely free to continue asking questions to all the speakers. Just preface the question with the person to whom you would like to ask it. And you can also like to ask a question to the general panel of speakers. Okay, so now we are moving computer science to the area between computer science and philosophy. That's where Thomas Icard works. So he did his Master of Logic here at the University of Amsterdam at the Institute of Logic, Language and Computation. Then he moved to Stanford to do his PhD. And his PhD thesis is called The Algorithmic Mind, a Study of Inference in Action, done under the supervision of Johan van Bintem. And I think Johan is also here in the public. And now he has been an assistant professor, an associate professor, and since very recently, he is a full professor of philosophy and also partly associated to computer science at the University of Stanford. The floor is yours, Thomas.
Great, thanks so much. Thank you so much to Balder and Rineke for organizing this. And I'm very excited to be in this session with these three scholars I've been so inspired by and learned so much from the work of each of them. So while I'm sharing my screen here, let's see, is that, no, that's not yet showing up. Okay, is that showing up?
Yes, now it's showing up, but it's not, yeah, now it's full screen, thanks.
Super. Okay, start my timer here. Super, okay, so the perspective I'm going to offer here is one from logic. What does this whole topic of causal inference look like from the perspective of a logician? And I hope to convince you that there are nice synergies between modern logic and causal inference that might be mutually illuminating. So everything I'm going to talk about here is a joint work with my PhD student, Guido Imbens. And we were asked to start by saying a word about what our working definition of causality is. And mine is fairly broad and sort of humanistic. I think of causality is the kind of glue that holds our understanding of the world together. So we kind of see the world in thoroughly causal terms, and we kind of can't help but think about causality in almost every aspect of how we understand ourselves and the world and our place in it. A little bit more, theoretically, what is a theory of causality? What should that do? Well, essentially, it should extract the essence of what it is for one type of event, maybe most saliently an action, to make a difference to another type of event in a very broad sense. So abstract away from other aspects of the world to just capture this sort of difference-making aspect of how things fit together in a broad sense. And so that kind of task has actually been taken up over the past decades across numerous disciplines, philosophy, economics, computer science, resulting in a family of really productive frameworks for systematizing and understanding causal conclusions, causal knowledge, how we can actually be justified in drawing causal conclusions from different kinds of data. And in that spirit, the main picture I want to show you for today that will come up multiple times during my talk is this one. So generally, in the problem of causal inference involves, I would like to argue, a kind of causal conclusion that we want to be able to draw. I'll give lots of examples of those. Some data that we have available to us, and some assumptions that we're willing to make that might go beyond the data in some sense. And there's many examples of each of these three different kinds of causal conclusions we might want to draw: bounds and causal effects, does X cause Y, does Y cause X, or neither, and so on. Different kinds of data regimes we might be in, and also different classes of assumptions that people have explored in the literature. And now the question I want to suggest is always of the following shape. We are interested in what combinations of these genuinely result in an entailment. And so I have the logical symbol. I don't know if my cursor is visible here, but okay, great. The logical symbol of entailment here, because really we're interested in the question, if I adopt these assumptions and I have this type of data, does the causal conclusion really follow in a very strong logical sense? So as instances of this, I want to give two concrete examples just to kind of motivate the picture before moving on to the logical angle. One is a classic analysis of Pearl 1995 of the so-called front door graph. So starting over on the right here, suppose we want to infer a causal effect. So I'm not going to explain any of the notation here. Hopefully you have a sense of it from the previous talks. I want to infer something about the effect of X on Y, a distinctively causal question. And suppose my data is kind of observational. It's just correlations, just probabilistic information about how X and Y and maybe some other variable Z relate, probabilistically speaking. The question is, how do I bridge from those observational data to an inference about a causal effect? And so this very nice idea is, one way to do that is to assume, if you can assume this, that X does impact Y, but it does so through an intermediate variable Z, and moreover, any confounding of X and Y doesn't have an impact on Z. If you assume that the situation that you're facing is one of this sort, then that little graph there actually implies a whole bunch of probabilistic equalities, such that if you put them together with the facts about the observational data, purely probabilistic information, that implies, in a very strong sense, a value for the causal effect, right? It sort of determines the value of the causal effect in really a logical sense that I'll make precise momentarily. Another example, also from one of our panelists, from Angrist and Imbens, 1994, is this local average treatment effect, where our interest is again in a causal effect, but we want the causal effect kind of conditional on compliance in the experiment. So we have some variable Z that represents whether assignment is, whether an agent is assigned to one or another condition. And we just want to know what is the causal effect among those in the population that actually comply with their assignment. Okay, so kind of harder question. And let's suppose, I'm not going to go into any details here, obviously, but suppose we have information about some, about the impact of Z on X and also about the impact of Z on Y from whatever means. It might be actual experiments. It might be something that is as good as experiments, as we've heard about already. And so now the question is how to bridge from that type of data to estimating local average treatment effect. And the beautiful idea here is these two core assumptions, so-called exclusion restriction and monotonicity, that I'm not going to go into, but you can sort of state nicely, are enough to actually bridge that gap from the type of data you have available to the conclusion that you want to be able to reach. So another very beautiful example of what I would actually claim is an entailment in a strong sense once you clarify the nature of those assumptions. Okay, so these are two examples of assumptions, data, and conclusions that you might want to be able to reach. And now, what is the logical angle on this topic? These are two classic kind of analyses. The logical angle is to make the syntax and semantics here explicit, right? So to make this into a general, a genuine entailment in the logical sense, right? So I'm going to say just a word about each of those. What could we take as possible semantics, as sort of models, and what could we take as logical syntax? And The semantics I'm going to propose is something like the following. We first need to be able to carve the world up into some variables, and we'll distinguish two different types of variables, the endogenous ones, which are the variables that we're interacting in some way. Those are the variables that we can query, or that we might observe, or we might change via an intervention in the system. And then there's also some exogenous variables, some aspects of the situation that we might not be interacting with directly, but that are nonetheless exerting some influence on the system of interest. And those are associated with a probability distribution. And crucially, each of the endogenous variables comes with a structural function, which tells us, as a function of some of the other variables, endogenous, exogenous, what the value of a given variable will be. Okay, so this is a fairly generic description of a causal setup. It's kind of hard to imagine too many examples of mathematical models of aspects of the world that couldn't be regimented in some such way. And so the underlying assumption is that whatever the causal structure is that we're trying to investigate, even though we might have very little access to it, it looks something like one of these. Okay, and Sara also already nicely went through this kind of hierarchy of types of distributions that one of these objects implies. I just want to recall that again. If we take the exogenous noise, P of U, and we sort of filter it through these structural functions under minimal assumptions, we get a probability distribution on the endogenous variables, right? So that's a kind of what we might call an observational probability distribution. It's what you would get information about if you were just passively observing a system from the outside. But these things also imply so-called interventional probability distributions. Those are distributions that you would get if you filter the noise through manipulated or intervened systems of functions. So for instance, taking some of those functions and replacing them with constant functions, formalizing the idea of an action on the system. And finally, this has already been discussed, but we have sort of counterfactual probabilities, which in the way I've presented it here are essentially just joint distributions over these potential outcomes, V of X, V of W, and so on. So they're asking, what is simultaneously the probability that I'd get a given value for some variables under all these potentially inconsistent interventions on the system. Okay, so a word is maybe worth saying why we call these counterfactual probabilities. And it comes from the kind of example that Sara already mentioned. Imagine we're asking a question like, for a patient who was given treatment and survived, how likely would they have survived if we had withheld treatment? So that's a quantity that looks kind of like this. We're conditioning on an outcome, a kind of conditional outcome that upon intervention, Y was actually the case. And now we're asking what would have been the case if we had done something different. And if you look over here on the right-hand side, the usual ratio definition of conditional probability, we're looking at a joint probability over two incompatible interventions. Okay, so that's why we call this third object a counterfactual probability. Okay, now we get to syntax, and we could have just tried to formulate one probabilistic logic, one logical language for talking about all of these at once, but we're going to find it useful to actually carve up the space of logical languages in a slightly more refined way. And we're going to introduce actually 3 probabilistic logical languages here. I'm suppressing all the details about probability logic for reasons of time, but the core idea is that L1 is going to be essentially probability calculus, classical probability calculus. It's the logic of observational probabilities. L2 is the logic of a slightly more complex type of object, probabilities that possibly involve interventions. So these interventional probabilities, and so imagine a reasoning system for reasoning about these terms. And finally, L3 is going to be the logic of what we've called counterfactuals. So these joint probabilities over a bunch of potentially different potential outcomes. Okay, so now back to why do we do this? Well, back to our core picture here, assumptions plus data, causal conclusion. The 2 examples that we've seen and many other examples like them are essentially, or can be seen as, a matter of going up in this hierarchy. So something like I have Li data, or data that I believe gives me Li information, and I want to reach an Li plus 1 conclusion. So I want to kind of go up in the hierarchy. And the question always is, what kinds of assumptions will allow me to do that? And our first example of the front door graph, we have observational probabilities. And the question is, when can we infer this? That's an L2 object, an L1 object. The question is, when can we infer this L2 quantity which involves these potential outcomes, this causal effect in this case. And we've seen an example of assumptions that would allow you to bridge that gap. In the other example of local average treatment effect, that quantity is an essentially L3 quantity, but we're assuming we have information that gives us essentially something we could encode in L2, right? So the question is how to bridge the gap between this L2 information that we assume we have and an L3 query. Okay, so in logic, we're often interested in showing that certain things are possible and using logic as a tool. Sara gave us a really beautiful example of that using answer set programming, for example, where formalization can help. We can also formalize these very examples, these famous examples from the literature. But another thing we often get in logic is showing that certain things are not possible, right? Showing the very limits of certain kinds of reasoning processes, reasoning possibilities. Think of uncomputability, incompleteness theorems, and so on. Much of what we get from formalization is indeed showing impossibility. So in that spirit, we might go to a very edge kind of question and ask how necessary these assumptions in fact were. So suppose we only had Li data, so data that would be formalizable at the level of Li, or I equals 1 or 2, and maybe also some Li assumptions if we like, but assume we have, for instance, the entire distribution at L1. When can we draw Li plus 1 conclusions, right? So this is a kind of question about what data imply what kinds of conclusions, but simultaneously, the way I've set it up, it's also a question about logical expressive power. So this empirical question has actually been transformed into a question about logic, and it looks something like the following. So here's a picture here in the bottom little circle is the space of L1 theories. These are descriptions of a situation at the level of L1, descriptions in the language L1. So you could think of those as essentially, observational probability distributions, if you like. And now at the above is L2 theories, so L2 descriptions of some aspect of the world. And the question is, so suppose I'm here in one of these L2 descriptions. I have all the L1 descriptions. I have all the L1 facts. I have all the probabilistic information. Sometimes we might worry that that underdetermines the L2 facts, right? In the sense that the L1 facts could be the same, but multiple different L2 theories project down to the same L1 theory, right? So that's one possibility. Another possibility is that knowing the L1 facts completely determines the L2 facts, right? So as long as I know all the probabilistic correlations and the joint probability facts, I can recover the L2 facts about interventional probabilities uniquely. Right? There's also a query relative version of this, so pick a specific L2 query and you can ask the same question. It's already been suggested multiple times today. You're not going to be surprised to learn that a first result here is that L2 never collapses into L1 in the sense that that gray area, the collapse set, is totally empty. So even in a query relative way, there's no case in which knowing the L1 facts determines all the L2 facts. And that's both, this sort of has this empirical significance, but it's also just a fact about logical expressibility, right? So L2 is everywhere more expressive than L1. Okay, and that's just a formalization of a strong version of the claim that's already been mentioned multiple times today, that correlation doesn't imply causation. But what happens if we go to L2 and L3? So here in L2, we have these interventional probabilities. It's the exact same picture. We have interventional probabilities and the theories of those. So all the facts about the interventional probabilities, where here we're imagining we've done all the ideal experiments that we could do. So we're getting all these interventional probability distribution information. And the question is, when do those facts uniquely determine L3 facts? So if I have a bunch of experimental data, when and when does that not completely determine the answer to an L3 query that is a counterfactual or related to that explanatory information that I might want to know about a situation? And here, intriguingly, the answer is actually that the gray area is not empty, right? So there actually are cases, both in a query relative sense and also in the general sense, where knowing the L2 facts completely determines the L3 facts. That can happen. So gray is not empty. But what we want to understand is what is the nature of this subspace, right? This kind of injective fiber here in L2 theories, in the space of L2 theories. What are its properties? How big is it? What can we say about it? And first result arises from putting a measure on the space of all causal models. And if you do that, you can show that while the collapse set is empty, it does have measure 0, so it's in some sense negligible. It's very small, right? And a follow-up result is that if you put a topology, not a measure, on the space of theories or on the space of models, you can show that the collapse set is topologically meager. So it's not just measure theoretically small, it's also topologically small. And moreover, via a connection between the specific topology that we put on the space of models and problems of statistical learning theory, there's a sort of nice connection between this topology and problems of statistical inference. You can show that this collapse set is actually unverifiable in a precise and strong sense. Roughly speaking, that means if we were in the gray area, even in the limit of experimental data, so all the experimental data you'd like, you still can't verify that you're inside that collapse set. Okay, so it's in some sense, this shows that the types of assumptions that you need to adopt in order to bridge the level from L2 to L3, those assumptions have to be quite strong, right? And we've seen examples of very interesting, but obviously in some sense strong assumptions that allow you to do this. And this just sort of is one way of seeing why that strength is necessary. Okay, so it's kind of an application of logical ideas to understanding this problem of, or these problems of causal inference. And I don't have much time to go back in the other direction, but as you could imagine, for the logicians in the audience, there are tons of new questions for logic that arise out of this connection. One that I won't go into in any detail is questions of axiomatization. So you might want to systematize the kind of reasoning that leads you from data and assumptions to causal conclusion. And that brings in interesting ideas from semi-algebraic geometry and other kinds of kind of new things for logic. Related to that, questions of complexity that are also very rich, but I'm also going to skip. The main thing that we've seen here is kind of going beyond looking at comparisons between expressive power of different logical languages, but looking at everywhere expressivity gaps, or almost everywhere expressivity gaps, and what can we say about that? So is it just this language is more expressive somewhere, or is it actually a much stronger sense of sort of everywhere in every model? As well as, we've seen sort of synergies, novel synergies that arise out of this between the kind of qualitative reasoning at the level of these potential outcomes or causal conditionals and the kind of quantitative reasoning that occurs in probability. And there's, of course, more. But I will stop right here and just thank you and say, I hope to have convinced you that there's an important sense in which causal inference practitioners are already doing logic. They're already asking and answering logical questions that are deep and rich, and making this sense a little bit more precise promises potential benefits in both directions. So I will stop there.
Thank you so much. That was really fascinating, and I think it does build bridges between logic and the other sciences. Thank you so much. So now we are moving from logic and computer science and philosophy to the philosophy of language. And let me introduce to you our fourth and final speaker of today, Katrin Schulz. She did her undergraduate degree in computational linguistics at the University of Stuttgart. And then she continued to go to the Netherlands to do a Master of Logic at the ILLC in Amsterdam. And then she did her PhD here also in Amsterdam with supervisors Frank Veldman and Paul Dekker on minimal models in semantics and pragmatics. And at the moment, she is an assistant professor at the Institute of Logic, Language and Computation of the University of Amsterdam and leading the Causal Inference Lab of this university. So the floor is yours, Katrin.
Thanks a lot. Thanks a lot for the introduction and also for having me in this workshop. It's great to be here. And in my talk, we will take, again, another perspective on causality. We will move, like the quote might already suggest, we move to causality in cognition. So that's actually what I want to talk about, causality in cognition. So how we as humans perceive the world as causal. And that's a different question from the question what causality is in the world, so whether there is causality in the world and what it means, or as it has often been described, the summit of the universe, as Maggie called it. So that's causality in reality. But we focus on causality in cognition. And these two things do not necessarily have to be the same thing. You can even imagine that we could even have a concept of causality without being there causality in reality. For instance, Russell has said that causality is just an artifact. Or people like Bett have called causality just heuristic that we use and that we can use very successful in surviving. Actually, some of the results that Sara mentioned seem also to point in this direction, that just assuming that there's something like structure already helps in some sense. Okay, but that's not what I want to talk here about today. What I really want to talk about is really causality in cognition. And we know that causality is very important for our cognition. It enables prediction, it enables making decisions, and then based on that, actions. We explain the world around us in terms of causality. So it's very important. It plays a dominant role in our cognition. And then, so it plays a very dominant role in cognition. And the question is, so from this it's not surprising that also our cognition is in some sense fine-tuned to enable us to acquire causal knowledge and to use causal information in a certain sense. And what I'm working on, so what we are studying is, how exactly does that work? So what exactly how do we acquire causal knowledge, and how do we use causal knowledge in our behavior and our reasoning? So that's what it's about. And then language comes in actually as a method, as an approach. So language as the window into the mind. So by looking at language, we can understand cognition better. That's the idea here, an approach that has been introduced already in the second half of the last century. It's very popular. So why language? Well, it's easily accessible. It's much more accessible than the brain is in general. And also language is really fine-tuned to our cognitive and social needs, and thereby in its shape and structure, it can also contain traces or mirror cognitive structure. And that's what we are looking for. That's why studying language in this sense is very interesting. Now, what are we actually looking at? So what are we looking for when we study language then? Well, what you can do is, for instance, really just study our explicit talk about causality. So what do the words mean that we use to talk about causality? And that can also help you tell you something about cognition, because if you understand the meaning of these words, that tells you also something about the model of the reality that we need to have to make the words work in the way they do. And that by tells you also something about how we model cognitively, how we model reality. For instance, one of my PhD students, Dean McCuff, he works on the words because and caused. There's actually a difference between these two words. And he studies the meaning of these words. And he argues that in order to model the meaning of these words, we need to assume models that differ from the models that are standardly now used in the literature. So structural equation models or Bayesian, causal Bayesian models, the kind of models that you have seen in the previous two talks. He needs a model, he uses a model that's a little bit more expressive. And he argues that we need this model because we need this model to explain the use we make of these words. And if we need this more expressive model to make sense of the meaning of these words, probably also we have to assume that structural equation models or Bayesian causal networks are not sufficient to model how we perceive the world as causal. So that's how this transfer from language to cognition can work. Okay, but there are also other structures in language that you can look at and learn about causal cognition in a sense. In the last couple of years, I have worked together with Robert von Roy on how we express generalizations. So how we talk about what makes the world around us regular, systematic, law-like. There are different constructions in language that we use to this purpose. For instance, we use generics, something like pit bulls are dangerous. We also use conditionals to express generalizations. If you heat butter, it melts. And there are also certain other constructions like habituals that we use to express regularities, something that we perceive as law-like. So Joseph Smokes is an example of a habitual. Well, now you can argue, so at least what we do is then we argue that also in the meaning of these expressions that we would perceive just as talking about generalizations, also these meanings contain a strong causal component. So also they actually talk about causality in a sense. Let me explain a little bit more one of these constructions, generic senses. So that's about senses like coffee is stimulating. Accounting for the meaning of these expressions is not easy. There are certain challenges that you have to deal with. I don't want to talk about all of them. Let me just mention one. And that's about the following thing. So generics express generalizations, but these generalizations allow for exceptions. For instance, I believe that coffee is stimulating, even though not all cups of coffee I ever had were in fact stimulating. A cold coffee, for instance, doesn't work that well. But generics allow for exceptions to different degrees. I believe that coffee is stimulating, but I also believe, for instance, that pit bulls are dangerous, even though very few pit bulls, in fact, are dangerous. So one of the challenges here is account for the different degrees to which generics allow for exceptions. And what we have proposed is that you can, you can describe at least the assertability of generics. So when you can assert such a sentence by measuring the relative difference. And that's basically just a frequency measure. So assume that we have a generic like G's are F. We then say that such a generic is assertable in case this measure of relative difference, which comes actually from epidemiology, is high. So that might look a bit complicated, but actually is quite easy. So the point is, just look at the numerator. The point is that for a generic to be acceptable, it's not enough that the feature has to be very common in the group, but it also needs to be distinctive. And that means that it is not very common in alternative groups. So that's what this numerator expresses. And then the denominator just relativizes to conditional probability. If the conditional probability of the feature in the group is high, then you don't need the feature to be very distinctive. However, if the probability of the feature in a group is low, the feature has to be very distinctive for the generic to be assertable. That's basically the idea of the measure. And that measure can actually account very well for the first challenge. So for the differences in exceptions that we see between different generics. So again, let's just focus on contingency because that's enough. You can now explain why, for instance, dogs bark is a fine generic because many dogs bark, other animals don't. But kangaroos have spots is not a good generic because very few kangaroos have spots, while other animals do have spots. Sharks don't eat people is not a good generic because sometimes sharks do eat people and they are not anymore, well, most other animals don't. But robins lay eggs is a good generic, even though only approximately 50% of all robins lay eggs, because it still distinguishes robins from other animals. And robins are female is not a good generic because that's not a distinctive feature. You can even explain sentences like mosquitoes carry malaria, why they are good, because even though there are very few mosquitoes that actually carry malaria, it's still distinctive for mosquitoes to carry malaria. So the measure seems to at least deal with this challenge very well. There's also other challenges that motivated to adopt this measure, but it seems to work. But then the question is, okay, why does it work? So what is it actually telling us about the meaning of generics that we can measure their assertability in terms of this frequency measure, this complex frequency measure? Well, basically there are two ways you can interpret this. One way is to say that the meaning of generics can be equated with the conditions under which we would learn the express generalization. And then it's the fact that relative difference is a measure that has been used also in the psychology of learning to measure how strong we associate, so how the strength of association. So in experiments that teach you to associate certain cues with certain features, you can measure this also very well in a relative difference. But we actually want to say it's more. It's not just measuring the strength of association, it's actually measuring the strength of the causal connection between group and feature. So we want to go for this interpretation. So we have this measure because what a generic expresses is, so a generic is acceptable in case there is a strong causal relation between group and feature. And it just turns out that relative difference is a good measure, is one way to measure the strength of the condition. And here we are building on a theory for causality in cognition that goes back to Cheng. It's from the 90s. And what she says is that we assume there to be certain theoretical entities that we use to explain the world around us. She calls them causal power. And so that's basically, it's unobservable theoretical entities that we assume, just like we also assume certain unobservable theoretical entities in physics. They somehow behave like probabilities, but they are not really probabilities. They rather express the capacity of I to cause E, for instance. You can also interpret them in the sense of Popper's propensity analysis. Okay, and then she says, okay, how does this work? Well, so how does causal powers that interact with frequencies? Well, people do not simply treat observed covariation as equivalent to causal relations. Rather, they interpret their observation of covariation as, well, basically manifesting these causal powers with the tacit goal to estimating the magnitude of these powers. So you make these assumptions that these causal powers are there. They govern the reality you see around them, and you estimate them both based on the frequencies that you observe. And then she shows that in certain situations, for instance, in a situation where you have only one alternative cause, you can actually measure, so causal power comes down to relative difference. Not going into this derivation here, that's not so important. And then Robert and I show that also in other very common scenarios, actually, you have this reduction of causal power to not only relative difference, but actually to conditional probability. Okay, so it seems that you can use certain frequency measures very well to estimate this measure of causal power. So that's then basically the idea here. So we say that we can treat, for instance, the meaning, we can account for the meaning of generics in terms of frequencies, and we have a probabilistic account for that. But then we give a causal interpretation of this account, and we're saying that a generic GSRF expresses how strong we believe that a certain feature is essential to a group. And that then, for instance, can also help you to explain certain problems that we have with stereotyping, which are also often expressed in terms of generics. Okay, so that's for the language part. Now let's go back to cognition. If we assume that the meaning of our generics can be estimated with these measures, does that also mean that we want to say that the way we acquire causal knowledge reduces to these frequency measures? And do we want to say that taking A to cause B basically comes down to, well, this admittedly complex but still just frequency measure, which is kind of also connecting to Thomas' talk. So do we want to say it's just the data, or how much do we have to add to get to the actual cognition that we see humans are able to do with causality? Well, in general, we assume that the idea is, many people have argued that's not enough. It's not just data for human cognition. There are other things, other factors that are also important. For instance, people assume that we are wired in a certain way that make us perceive information in a certain way, that we learn to learn reason causally from that. In a way, you could say that's also already hidden in this Cheng approach. We assume these causal powers to be there. We assume these causal powers to explain the world around us, and then we estimate them based on the frequencies we observe. So there could be certainly causal structure that goes into our cognition of causality. And then people have also argued something like social interaction matters, communication in particular matters, and let's not forget interaction with the world also matters for how we cognize causality. And that goes back to the notion of intervention, for instance. But now the question is, what exactly do these different factors contribute? How do we work together? How much structure do we have to assume? How much social interaction communication do we have to assume? How important is the fact that we interact with the world? So that's about, if you think back to Thomas' equation, that's about the extra assumptions that we need to make so that together with the data we can derive causal conclusions. How does that work in a human case? That's here the question. And people have run experiments on that, trying to figure out what exactly the contribution is of the different factors. But the problem is these experiments are normally run with humans, and that means that you cannot control all the conditions. In particular, you cannot control the cognitive structure. It's always there, full blown, it's there. So I think that what we need to do here is work more with computational models. And that doesn't mean actually that we have to build these models from scratch. They're also already interesting models to look at and to study, to understand this interaction better. Well, in my case, because I'm looking for a language, a good model to start with looking at are, for instance, large language models. They have, I'll show you that they have frequency observations based on the training data that they see. We don't have full social interaction, but we're looking at communication. So some of the communication goes also in, limited. They have a very limited cognitive structure, and we know exactly what a cognitive structure is that goes into these language models, and there's no interaction with the world. And the question arises, given that this is what you have, how much can you already learn about causality from this information? Are large language models able to do, in some sense, in some respect, already what we are able to do with causal, in our causal cognition? Do they behave similar to us when it comes to causal reasoning? That's the question here. Okay, and that is a question that has been studied recently by different groups. I want to mention one paper here from Imbens and Schulz from last year. What they did is they basically ran a couple of standard psychological reasoning tasks also on large language models. In particular, they used GPT-3. So basically, we have fed GPT-3 exactly the same input, vignette-like input that were used in these reasoning tasks in psychology, and we looked at the responses of GPT-3. So what did I find? So it's GPT-3, as already mentioned, that basically if you feed the same vignettes that have been used in these psychological reasoning tasks causal reasoning tasks to the GPT-3 model, it performs very well. So you get very high scores. However, the results are very brittle. So if you change the vignettes a little bit, already the performance goes down a lot. Now I have to say here that that has to be studied more systematically. We only studied a couple of we only did a couple of experiments, a couple of disturbances, so that needs to be studied very systematically. But it looks like right now, this looks like it's only parroting. So because these papers have been in the training data of the large language model, it's what you get back. We also run a couple of more behavioral experiments. So in this case, basically we transformed an experiment into text that we could feed into GPT-3 and then look how GPT gave the answer. But in this case, GPT is not trained on the exact vignette. So it's not trained on the exact input, cannot be. And their performance is very low. In particular, we looked at whether GPT-3 is able to make the distinction between doing and observing that is so important for human cognition, and where we know that humans seem to be able to make this distinction. Just to give you some idea of what they did, you don't need to read the text, but basically you have a couple of observations. Then you get an explicit description of the causal network that varied between a causal chain and a common cause structure. And then you were asked to make prediction. And basically there was a difference between whether you observe B to change or whether you get an intervention in B. Yeah, so B is wriggled or just observed to be different. And then the question is, would you see a change in C? Okay, and what we found is basically, and now you have to focus on the blue bars. So that's GPT-3 performance. GPT-3 is not able to see a distinction between both causal scenarios. So the performance in both scenarios is basically the same on all tasks. And they concluded from that GPT-3 is not able to make this distinction between observing and doing. I think we should be a bit careful here, because what you can see is that it does make a distinction between doing and observing. It just cannot take contextual information about the causal network into account, at least from this one test. But again, it's only one test, so that's something that needs to be studied more. But it doesn't look, so far it doesn't look so good. We were looking at something different. We wanted to see whether you can find what has been often described as content effects in large language models. So this is a general pattern that we see in reasoning tasks with humans. So humans, when they reason about abstract reasoning tasks, they often take into account information they already have about the world. And because they see the world as they interpret the world causally, you also see this effect for causal information. So they take into account causal information that we already have, and that biases their performance on certain reasoning tasks. And the question is, can we see this also in these large language models? And we thought there might maybe we do, because there has been also a recent study where it has been shown that some of these content effects can be found in large language models as well. And this study, they used a different model. They used chinchilla, and they had a couple of inference patterns like syllogisms, very famous Bayesian selection task. And what is important in these tasks is that, so what we see is that humans are biased in these tasks because they take into account their priors. So I gave you a couple of these inferences. So basically very roughly, what you see is that if the priors are high, then we also think the inference is valid. If the priors are low, they think the inference is not valid. If they are neutral on the priors, it's somewhere in the middle. And they found that these particular content effects you can also find in large language models. They have exactly the same kind of disturbance biases here, which might not seem so surprising because, well, they have, at least it seems like they're learning the same bias that humans learn. And then they also use them in these inference patterns. And this is just, again, it's just about covariation of frequency data. It's just correlation that is responsible for these prior biases here. Okay, and we were wondering whether we can find similar effects also for causal content effects. And here we were looking in particular at one study from Cummins. That's a very famous study on causal content effects. She gave humans basically conditional inference tasks. So tasks like modus ponens, modus tollens, denial of the antecedent, affirming the consequent, where you get first a conditional, then you get one of the senses in the conditional, you're asked to reason for the other. And some of those are valid, and modus ponens, modus tollens are valid, the other two are not. And then, so that's the pattern. And then she had conditionals that are causal conditionals, where she only used causal conditionals, either reasoning from cause to effect or from effect to cause. And she were looking at whether our assumptions about disablers, number of disablers, or number of alternative causes for these cause and effect relations would actually influence our performance on these inferences. And it turns out it does. So what you can see here is that the causal model that we make of reality also impacts, so like you could say the causal priors that we have, they impact our reasoning on these abstract reasoning tasks. And now the question is, do we find the same in large language models? And that's something we are working on at the moment. So the idea is to try to replicate Cummins, but then use a larger pool of examples containing also other types of conditionals. Conditions, should say conditionals here, so common cause, purely probabilistic, no connection, and then see where we can see that the performance depends on causal information, so that we can see causal content effects. That's something we are still running at the moment. I only have some preliminary results for you. So that's what so again, we used GPT-3 here, and we did few shot training on GPT-3 because that has been, it turned out to be quite useful for reasoning tasks if you run it on GPT-3. And what you see is some inferences. So what you get here is the portion of answers that are counted as valid. This is the number of shots of training, from 0 shot training to 5 shot training. And then modus ponens is red, modus tollens is blue, denial of the antecedent is purple, and gray is the affirmation of the consequent. You see it gets modus ponens red correct right from the beginning. And it also thinks that affirming the consequence is valid from the beginning. But the other two inferences, it thinks it's invalid at the beginning, and then it turns to valid. Okay, what is interesting about the pattern is the following. This is actually human-like behavior. Humans also think kind of all these inferences are valid on average, because most humans give to the conditional and biconditional interpretation these tasks. And that's why you get this. So this is also what the end at the after few shots, after 5 shots is roughly what you also see in Cummins. Interesting is that these already start out being valid. Why? For these, it had to learn that they are valid, the future training. And these are the inferences that contain negation. That might not be so surprising, because we have seen that the language models have issues with negation and other tasks as well. So, but for these tasks, the future training really helped. However, we did not find so far, at least for the few examples we have from Cummins, we do not find any effect of causation. So there is no order effect here, for instance. There's also no effect of a number of disablers or a number of alternative causes. So in general, so far, what we can see is we cannot really find traces of human-like causal behavior in these large language models. But again, this is only preliminary. This is something we really need to start in more detail. But so far, it looks like frequency data and the very few, the little bit cognitive structure that these large language models have, and a little bit of communication they see, is not sufficient to develop the human-like behavior, at least to some degree, human-like behavior when it comes to causality. Okay, now I think I'm at the end of my time. Let me just thank my collaborators, and yeah, thank you for listening.
Thank you so much, Katrin. And very timely results containing comparison of human cognition to large language models. That's really great. So now we are going to start our general discussion. And both Balder and I will read aloud some of the questions that you as attendees put into our Q&A. And I would like to start with a general question, which was asked by Faye Oosterhof. And she asked, when using statistical inference for concluding causality, isn't it logical to always conclude it is not, so there is no causality? An instance needs to be prerequisite for something to happen to be actually causal. And it seems like we are talking about incidence affecting factors, not causality. So who would like to take this challenge? Anybody dares? Not Sara?
So let me say something. This was, in some sense, a little bit of what I was trying to address at the beginning, where economics nowadays is often about just trying to answer fairly simple, well-defined questions, that are difficult to answer, but where the questions are very well defined. David Carte was trying to figure out what does raising the minimum wage do to employment. In other work and in work by Angrist, they were trying to figure out what happens if people get more education. Do on average their earnings go up? And so in all these cases, it's relatively easy to imagine what a hypothetical experiment would actually look like. And what we're after is essentially the answers we would have gotten had we done an experiment of that type. And the challenges kind of we're dealing with are the fact that it's not easy to do that actually experiment. It's not ethical, or it's not feasible. It's too expensive. And so we try to make do with observational data. And so we get into these problems that there's selection, there is endogeneity, there's other reasons why these groups may be different. But it's not really an option to say, well, we should just never conclude that there is any causal effects. We're trying to help policymakers make decisions, and they would like answers. They would like the best answers we can give them to make better decisions, rather than wait for perfect answers there. So I feel just saying, well, we're not really completely sure, which is true, but that's not going to help us actually move forward and making decisions. In some sense, kind of, so that what you saw during the pandemic as well, there was a lot of uncertainty in some of the science, but we do have to governments, the political authorities do have to make decisions, and we're trying to come up with good answers based on the best science.
Yeah, thank you so much. The next question is also directed to all four authors. It's by Thomas, and he asks, after hearing all the talks, it amazes me that a component of time appears to be very implicit in the proposed reasoning. How do the authors see this? Who would like to start on that one?
In some of the work we were doing, there was an explicit time component. So we had dynamic Bayesian networks, so there was time there. And we did use the fact that we assumed there were no instantaneous effects, and we assumed that there was, all the causal effects were going from time t to time t+1. So definitely this is a useful thing to model for us. I'm sure other speakers also want to say something.
Mm-hmm. Thank you.
Yeah, I mean, I think it is implicit kind of in most of these problems. Kind of, if you say, well, what is the effect of education on earnings? We're looking at the effect of getting more education now on earnings later. Or when Cate looks at the effect of the minimum wage, it's about changing the minimum wage today and looking at the effect on employment next year or 2 years from now, whenever. But the time is always the big component there. This is not, this is not like the causality sort of in quantum mechanics, where there's sort of complicated things happening at the same time. These are much more mundane questions where time is clearly of the essence, and it's sometimes left implicit, but it's definitely there.
Would anybody else like to continue about time?
Maybe it's just worth saying that there's two things you can do. One is leave it implicit, which seems to be very useful and the right thing to do in many cases, or you can make it explicit, as at least happened in Sara's talk and in lots of other work as well. So there's different choices there, and probably depends on the problem you're trying to approach.
Yeah, many thanks. So the next question is actually related to Balder, to the introduction. So it is a question by Werner Raup. And he asks, when you write deriving causal knowledge from observational data, what do you mean by deriving? Is it more than trying to be as careful as possible when testing assumptions on causal effects?
Well, I guess what I was trying to say is I was trying to set things up in anticipation of the talks that we saw later, with reference to the fact that, as Thomas mentioned in his talk, for example, how Pearl describes this, that there is kind of a jump that you have to make to go from level 1 to level 2. If you have only observational data, but you want to make causal inferences based on this data, this requires additional assumptions, which is a theme that we saw I think in most of the talks today, and which is of course also very much related to the contributions of Guido Imbens that led to the Nobel Prize award, where the assumptions take the form of natural experiments. So I think this was a theme that we could very clearly see throughout the webinar today.
Thank you very much. And hereby I hand over the baton to you to ask the next questions from the attendees.
Sure. Well, I saw one question. Let me see if I can find it in the chat. One of the audience members was asking if the panelists have any suggestions for good books to read about causality. So Pearl's book on the Book of Why came up, which the questioner mentioned also. But maybe panelists can give some recommendations for general reading on the topic. Somebody wants to make a suggestion?
Well, Professor Imbens has a book, right? So I guess that's the beginning.
Yeah, I mean, I think there's a lot of books these days. I mean, I think Pearl's books are definitely very interesting. For the Book of Why, I actually wrote a long essay kind of discussing that, and it's sort of why in economics it hasn't attracted as much attention or following as in other disciplines. And that goes back a little bit kind of to the slide I put up with that Moniac machine. I think there was a time when econometricians would build these very elaborate models that look kind of like some of the directed acyclical graphs in the Book of Why, where that sort of rely on lots of assumptions. There's a lot of moving parts to these models. There's lots of assumptions that need to be made to make these work. And people became a little skeptical of how well these things worked in social science settings, because in the end, kind of the type of assumptions that these models rely on, which are always kind of these exclusion restriction forms, where some of the arrows are absent that could possibly be there. And those are very often very hard to justify in social sciences. And so these very complex models make a lot of these assumptions, and as a result, the inferences coming from them can be very sensitive. And so the kind of there's a bunch of papers in economics in the 80s that kind of started questioning how reliable these models really were, and what sometimes is referred to as the credibility crisis in the empirical work in economics. And so then kind of people focus on simpler settings where there were more modest inferences possible, but more credible ones. And so that's kind of partly why some of these complex graphs have not really gotten much traction in economics. So, but the type of causal inference that is prominent in economics is more of what is sometimes referred to as the potential outcome form. And so you see some of that in the book I wrote with Ruben, but there's some other books that kind of take similar perspectives. There's a nice one by Scott Cunningham, an economist that is very accessible. And but in the book by Jamie Robbins and Michael Hernan that I think is very good. But but clearly Pearl's books are very very important too in this literature.
Thank you. Oh, Thomas, you wanted to chime in on this too?
Just to mention one big one that hasn't been mentioned that might even address some of the questions that we might not have time to get to that were raised in the chat. There's a nice philosophical treatise on causality by James Woodward, called Making Things Happen, which addresses a lot of the sort of philosophical foundations of this broadly, this broad sort of picture of causality as a matter of manipulation and control and intervention.
Thank you. Well, we can cover maybe a little bit more. But we'll definitely not have time to go through all the questions, but I'll just try to pick some. There's a question to address to Katrin, which is asking, is there a relationship between the frequency measure for generics and causal power and other measures for causal effect strength in the literature, such as ATE, average treatment effect?
So as far as what I know of, I have to think about it. But so what I know is that there's a relation of causal power to causal sufficiency, as it has been described by Pearl. So that comes down to the same thing. So there's a relation. For the others, I'm not sure. I would have to think about it. Not that I know.
Sure.
I could say something about that would be helpful. So I mean, like power PC is basically average treatment effect over the probability of the effect of the absence of the effect given absence of the cause. So it's kind of like, you're putting a further term in there, and that's has all the important features that Katrin already discussed.
Thank you. There's a question here addressed to Guido Imbens. How to deal with selection bias when trying to infer causal relationships? I can imagine that some people are more likely to buy lottery tickets than other people. Is the causal finding then only applicable to a selective population?
Yeah, so there's two things there. One is the selection leading to differences between the treated and control observations in the sample. And there, so we relied partly on the fact that the lottery obviously is random in which lottery tickets actually win. Then kind of in the empirical work, we still needed to do more, because the fact that some people buy more lottery tickets than others means that there were still differences between people who won large amounts of money in the lottery and people who didn't. So that's one thing. And we use various adjustment methods, and even more importantly, we showed that these adjustments actually worked kind of by looking at what was happening to people's earnings prior to winning the lottery as a way of validating these methods. But then the second thing is that obviously the people who play the lottery may be different from the rest of the population. And clearly we were not really interested in what the effect was of a universal basic income for people who played the lottery. We were interested in that from a policy perspective for the whole population. So the question is whether that study had much external validity. And so in general, and kind of this is in line with a lot of the social science literature on this, going back to the work by Cook and Campbell, we view the external validity part as much less important than the internal validity part. We're really trying to get the causal facts right, even if it's for a selective population, than worrying about the getting the population right. And that's, of course, that's also what the Food and Drug Administration do in drug trials. They don't insist on the population for their drug trials to be representative of the population. Partly because it's very difficult, because you need informed consent, and people who give informed consent are not going to be the same as the general population. So you can never guarantee that your study population is representative of the population as a whole. You can try to address that. You can look at characteristics of the population you're studying and see how much they differ in terms of age, education, lots of other things. And for the lottery study, we found that actually these populations don't look so different after you adjust for some background characteristics. So we didn't think in our case that was a particular concern, but it's one of these things that makes these studies always have limited validity. And we would try to do better there, but it's hard to guarantee that the study population there is representative of the population we're interested in. and we do a whole bunch of things to assess whether that's a problem. If we find that the treatment effects actually are fairly homogeneous, then it's probably less of a problem than if we find that there's wild variation in these treatment effects. But you can never guarantee these things. This is kind of where empirical work in social sciences is always going to have concerns, and you're trying to do the best you can, and you're trying to show as much as possible that the methods do actually work in the cases you're studying.
Thank you very much. And I think we are out of time, unfortunately. So let me just take this opportunity to thank all the speakers one more time. I think this was a very interesting program with lots of cross connections between the talks, even though they came from different angles. And thank you very much for the KNAW for supporting for the organizational support for the running this webinar, and thank you everybody for joining in and asking interesting questions. I don't know, Rineke, do you have any other words to add?
No, I would just like to join you in thanking everybody, both the speakers and the public.
So this webinar was recorded, and it will also be made available later on if you wanted to rewatch it or share it with other people. I think it will be made available on YouTube. I don't remember exactly, but I guess
correct, Balder.
Okay, thank you. Great. All right, thanks everybody.
Thank you.
Thanks. This is great.
You.
So
Bye.
we're
Thank
going
you.